Welcome everyone and thank you for joining us for the second webinar in our series on imaging. I'm Abdullah and I lead the imaging team at 10x Engineers. It's a pleasure to have you all here today. So we have Craig Sullender as our speaker today. Craig is a highly knowledgeable expert in image and video processing with experience working with leading companies such as Apple. His deep understanding of camera technology is widely recognized and respected in the industry. Craig has been involved in the development of raw image processing algorithms and their implementation in both software and hardware. Known for his creativity and credibility in R&D, Craig's advanced work on machine vision at the pixel level has been particularly impressive. So please join me in welcoming Craig. Thank you, Craig, for agreeing to speak with us today. We are eager to hear from you, and over to you.
Part of this set of slides is what I was using for presentations. Part of it is some things I pulled out of my old work that I thought might be interesting to you. And I was really hoping we get a chance to discuss how a small machine like this could be used within a machine learning system or on chip with a camera. And so the name of the technology is ChipSight. And I'll give you a little bit of my background here. There's people, I included that. That was a door camera we made a few years ago at an incubator in San Francisco, Highway 1. And we managed to time it just right that we were developing this when the Ring camera came out. So it was awesome timing. In top left, I have some sensors on the space station's power system. The top, you see some iris recognition work I did. These heat maps on the far right are something I came up with to look at which part of the iris was matching and which wasn't. And so with the reason people would like to use iris recognition is that you get 1 in 50,000 security. So like out of 50,000 people, you should be the only match. If you use both eyes, it's like 1 in a trillion. So it can be pretty secure. The difficulties are using a cell phone camera. It has such a short focal length. It's hard to get a good shot of the iris. And you can tell looking at these that these are sort of blurry looking irises. And so even with this level of blur on the iris, we were still able to do the biometric matching. Then this one that looks like it's in water here is a subsea robot I worked on in Houston. And I was working on the sensors on it. It has structured light, has a 3D camera at the top in the head there, and then a structured light sensor that uses a blue LED projector. And then it has these the body opens. After it goes underwater, the body opens up and these arms come out and they can grab things. So it's used mainly for oil work. So my goal when I was working with cameras, they were a little bit difficult to work with and very specialized per application or per market. And so my goal was to build something that could be used anywhere. So for any application. So I knew it had to be pretty simple, general purpose, more of a hammer, say, just kind of a dumb machine tool, something small and simple that could provide the pixel processing needed for higher level applications. And just let me know if I should slow down or cover any other questions. The overall idea is to group multidimensional data. And so with image processing, most of the time if you're not doing some kind of image enhancement like filtering, and even with some kinds of filtering, you're still interested in the objects of the in the image. So if you look at the patents or technologies for different types of noise filters and other types of filtering, they still, it's like half the time they still want to know what the objects are, where they're located, what details are important, so that they can do different types of masking and work on different parts of the image. So in other words, people want to make more intelligent processing that takes into account what's in the image. So I had this list of goals. Looks pretty smart. It's all after the fact. So I came up with this afterwards. As I was working on it, I just kind of took it one step at a time and said, yeah, this needs to be very simple. This needs to not have a big inner loop. This needs to have, to boot up and work well, even if it doesn't know any context of the scene. And one of the most important parts, along with the simple inner loop, like not having to make too many decisions per pixel, was that the last point on that list is that it have adjustable resolution. So there's cases where you want the fine details of the object in the image, and there's times when all you need is a box around it to say there's something there. And so I wanted to be able to smoothly adjust all the way from pixel resolution to full region resolution. A few of these slides are going to be kind of basic. They're just showing some of the parts of image processing systems. In this case, maybe a camera, an FPGA, or an ASIC, and a processor. And we'll talk about that some more, but the main idea here is that you want to do the simple repetitive functions in hardware and not software. This goes into that a little more with a range of complexity there, from pixels to features to regions to objects to something like tracking or recognition. And so trying to do all that in software is the easiest thing, and it's why people buy, say, and I'll go back to the type of vision sensors I was working with on the subsea robots. All of them had a Jetson in them, and that's just the way it is. Just like drop a Jetson in, have some sensors, write some code and go. All you need are software engineers. But it's workable from the point of view that you can hire some software engineers and support a product. It's way inefficient and expensive, but it's good enough that that's what people do. And also really not appropriate for consumer products. So when we kind of span the range between these really high-end sensors that cost $500,000 to wanting to build a sensor that costs $1 and still produces good information, you have to change your thinking, and you have to look at it, every bit of it, with an eye towards efficiency and optimizing it in some way, or understanding what the real problem is at the heart of it and solving that. And so the problem I wanted to solve was that pixel data is just too much. There's too much pixel data, and what we really want is information. We really want some information about the groups of pixels that make up surfaces or details or objects. And then talk a little bit about an ISP here. You guys know what an ISP is, so you don't really need to know this. But the point I was making in my presentations was that we tend to look at images that have been processed through an ISP, but you also have the raw pixels from the camera, and those can be used to do machine vision. Still continuing the argument. Had to repeat this a lot for people. Sorry, same thing. I'm going to skip through these kind of quick, but here are the ideas that you could use this pixel grouping machine with different kinds of input. In fact, it doesn't even have to be pixels. It could be any kind of multidimensional data. And this is a little bit about how it would be built out as a standalone piece of hardware. There's, if you don't do like full segmentation as part of it, there's really easy things you can do. You might just be looking for motion. You might just be looking for color. In building controls, it's simply motion and background subtraction and just looking for what's moved and count how many people are in a room. So this is the inner working of ChipSight. It works off of 2 lines of image data, so you don't need a frame buffer. You just need enough on-chip memory to hold 2 lines of the image at a time. And so you're working with a raster scanned image data, so you're just taking it 1 line at a time as it comes from the camera. There's a couple of stacks of memory to hold the regions that you collect as you go along. So that part labeled state machine in yellow in the middle there, the vertical box, is moving left to right and making associations between the segments that belong together. And one of my goals was to have the inner loop of that be very simple, and there's not a whole lot going on there. It's looking at the pixel below it and the pixel to our right. So it's looking at the next pixel plus the pixel below it and making a relationship and deciding if they belong together in the same region, or if it's time to start a new region, or if they're part of the same feature or sub-extent. So the reason for breaking it down from just a region is that the old method of locating objects or doing what connected component labeling was used for. It's like if you had a segmented image or segmented in some way, like if you have a range image that is presenting pixels as distances, then it's pretty easy to say, well, this area that's all at 2 meters is part of the same object, and then this area that's behind it at 6 meters is another object. And so it's easy to see those and to tell where they belong. But if it's a 0.5 megapixel image, it's still a lot of data to go through. To make it understandable for the higher level program, you want to mark off and locate those groups that are together in distance and report those in some kind of simple list for the higher level algorithm. And it's just not the way people tend to approach this. They tend to spend a lot of cycles going through the whole image in a process that may have to make more than 1 pass. It may have several operations per pixel. And if they start tracing the outside of an object, then they have to take a walk around it, making decisions at every pixel of which way to go to keep walking around the object. And even then, you don't get all the details, you just get the outline. Or a box sometimes. This is one of the diagrams from the patent showing prior art where the region is marked off with a box. And so the object on the left is supposed to be something like a figure 8 or something with some holes in it. And the way ChipSight does it retains all the details. So it retains the holes and breaks it up in a useful way. But those pieces that I call features are still related to the same region. So the list is just as valid for the region. And this is an example. It's a pretty simple output with regions and subextents. And if you see over here on the left, it looks like I made a mistake with the math because this one was 1 pixel wide. So I called it size 0, which isn't right. Abdullah, tell me if you need me to stop
Uh,
on any of these.
So I think let's go through this one example so that we'll understand that how these regions and features are being made.
Okay.
Yeah.
Okay, let's see if I have anything. I'll show you a couple of more things I've built here. So here's some that I had built. This one has a lattice FPGA on the back. It's like a 25 millimeter board. And then this one was done in software on an ARM. And this one has one of the little camera cube. Can you see that on the green board? It's like a
Yes.
3 millimeter camera. That was fun. So I worked with Arrow and Aptina gave me these parts, and I made it so that it would kind of plug into one of their dev kits. Yeah, so the idea of the variable resolution is important because you don't always need full resolution. So if you look on the right, this would end up being what, a handful of bytes to say where these areas are, but you would still be able to track the balls. And if you were doing something that needed to recognize like it's a person or it has 2 arms or something like that, then you need more resolution like the one on the left. And there's some more demos I did where I had a projector and the camera watching a person's hand, like grabbing the image icons and moving them or changing the size of a window. And these are on YouTube. There's a chip site area of YouTube that you can see these. Lane departure, something else. Okay, one more example of the variable resolution I have to show you. So like, for example, something like this is not enough resolution to tell what this is, right? But then as you increase the resolution, it gets to the point where it's useful. So you're going from what, 100 bytes or something to define these to, thousands of bytes, but you're still not up to tens of thousands of pixels that you need to deal with. I don't know if you saw this one I did for a conference, and the way I presented it at the conference was only the lowest resolution one first at the top right to make the point again that there are times when you don't need all of the information that you have. You just need enough to tell for the machine vision application to do its job. So by the end, you can tell it's fish. Let's see. Yeah. And this one shows a little bit of the inner workings. So it has a video at the top left, and I did some really simple segmentation on it. The bottom left is chip site working on breaking these regions up into pieces. And then the one on the bottom right, I redrew back in with the region information. So at this resolution, it's very little data, but it's enough to do lane departure warning. And again, you probably would never use it in this fashion on the bottom right, but it looks kind of good for a demo. Okay, that was it. So let's see, you want to go back to, let me go back.
Like if you can go through one examples where how from the raw data, how the
Right.
yeah how
Okay.
it decides for that this is a feature or region, and then I need to couple them together. Just one example or somehow so that we can
Sure. Yeah.
understand. Yeah.
Yeah. So you have to already have the rule you're going to use to tell what you're looking for. So maybe you're looking for something of a certain color, or maybe you're looking for something that's a certain type of edge. But this machine is not intelligent. It's like I said, it's like a hammer. It's only going to do what you tell it to do. So the simplest would be something like the range image, where each pixel represents a certain distance. And you can easily say, everything at 1 meter belongs together. Everything at 1 meter that's co-located, they're neighboring pixels. I know, it's a vertical piece at 1 meter. That's what I'm looking for. And so I know I want to group those together. And so then as the machine is scanning there across the two rows, it makes the connections when it satisfies that rule. So 1 meter or something that's close enough in the range distance, it's going to collect those together. Some other distance, it'll collect those together in a different region. And it does that in one pass as it looks across the pixels like this and the two lines. And this is a four-way connection, so it only has to see the pixel ahead of it and the pixel below it. So the labeling process is really simple. It's just issuing numbers starting with 0, and I'm just labeling regions as I go. So after I find a region that I'm interested in, I call that 0. The next one, if it's not connected, I call it 1, and just keep going. And so these are loaded into linked lists. The linked lists keep up with these subregions belong with the larger regions. So there's a bit of housekeeping going on. There's some juggling of the linked list going on. But again, it's all in a fixed number of cycles. It's deterministic. So the worst possible detailed shape you can think of, or the most number of objects you could put in an image, it'll work the same way. It'll be done by the time you get to the end of the image. So by the time the last line of the image arrives, you're done no matter what has occurred in the image. And yeah, I guess, I'd probably have to do something animated maybe to really show it working. Maybe I could do like a little animation of the thing going across, feeding in an arrangement of pixels. That might be good.
So actually, it's just so based on some criteria, it's just labeling the data that each subsequent pixel belongs to, and can it also be multi-criteria? For example, one sort of segment. So I am just using segmentation. So one sort of feature extraction based on color, the other feature extraction maybe based on the distance, or like.
Yeah.
You understand?
Yeah. You could. Yeah, I mean, you would just have to decide which parts you want in the same region. So if you want those all in separate regions, that's pretty easy. Yeah. Another thing you can do with it is you can do 3 dimensions. So you could do either like a sliced object, or you could do a series of images like a video going through time. And it's the same method. So In that case, you do have to store one frame. So then you would need the past frame plus 2 lines from the new image. And so if you can imagine behind this, there being one frame that you're of an old image, you're going down at the same time, and you connect through at the same time. You're doing 1 pixel to the left, 1 pixel down, and also behind it, so to speak, in the past. And so you can do 3 dimensions. I imagine you could keep going and do more dimensions. I just don't know how to hold that in my head.
And now just thinking of another, like, so for the motion estimation kind of problems where you estimate motion for 2 frames, where one frame is a little bit displaced from the other, that would be that would be an example of 3D. Or we can.
Yeah, I guess I hadn't thought of that. I was thinking of kind of like a CAT scan or something that's a sliced object to make it 3D, or an object moving through video in time. In this case, if the object was overlapping, it would be so easy to track, right?
So we just need to measure the delta, that how much overlap. So for example, in one image, it's only this much the object is. We just need to figure out that this is actually how the images are aligned, because actually motion estimation and image alignment using those standard, like you said, that software algorithms is quite a challenge. So I am just thinking that even if we do it, as you discussed, that we can do it on multiple frames as well, it will be just we have to store one frame, and like doing that, understanding only, and the information that we are actually interested in is very little. So that how much is displayed. So I think that would be the good area where we can deploy or use that.
Yeah. And so one of the tricks you can do here to help with that is, it gets a little more complex, but you just extend this area you're looking at a little bit. So in other words, let's say you have a region like this. So instead of making it exactly the size of my hand, I would make this region and then I would expand it a little. In other words, I would just pretend it's larger than it is, and then it's easier to overlap with something that may be a little further away.
Got it. So adding a little bit tolerance as well, so that we don't miss. Just don't draw the boundary line exactly such that even if that's got it. So I think any other questions, guys? I think let's open for the questions and the discussions. So,
at this company I'm working at, they always put out snacks in every meeting room. And I think that people come to the meetings for the snacks. And we can't have snacks on a Zoom meeting, so it doesn't work very well.
So I think, in the next meeting, we'll have a coffee and some snacks, so that.
Right.
I was thinking, can you hear me?
Yeah. So
I was thinking that in doing your processing with the images, how much of the pictures that you took, you thought that those pictures should have the high dynamic range in them for your processing to work better?
That might work well for HDR, because HDR cares about regions. So I think you're interested in the low frequencies and compressing the range at the low frequencies. I hadn't thought about using chipsight for that, but when you look at most image processing, when you look at it, there's always a way that knowing where things are is going to help you out. to do a more intelligent type of filtering or processing. So I'm not sure. I mean, with HDR, I think, don't you use masks? Do you mask off parts of the image for HDR to do the compression or not?